Hello, thank you for the opportunity for me to present today. My name is Axel Kaliff and I am a research engineer at the division of RPL at KTH in Florian Bokorny's group. My previous work has centered around improving the reproducibility and scalability of robot experimentation, resulting in one study currently submitted to RAL, which is focusing on the effectiveness of random exploration data for visuomotor policies, as well as another study which is currently in the works, aiming for ICRA 2026. And this study aims to increase the efficiency and safety of real-world robot actions through cloud-native simulation in the loop. Both of these studies have required large-scale data collection, for which I have developed an automatic data labeling and environment resetting framework called AutoGrasper. And this framework and toolkit was presented at an IROS 2024 workshop about data collection using embodied robots. During my time at RPL, I've progressed a lot as a researcher, and I'm very excited to bring that perspective into the topics of this field. So moving on to a central challenge of this field, which is alignment. The dominant paradigm for aligning large generative models have been reinforcement learning with human feedback, or RLHF. This is a multi-stage pipeline where a separate reward model is trained on a dataset of human preferences. Then an RL algorithm like DPO is used to fine-tune the policy to maximize the score from this learned reward model, while a KL divergence penalty term prevents it from drifting too far from the initial model. The RL stage is a significant practical challenge and also often involves training multiple models, and the on-policy sampling required by PPO is computationally expensive and can be unstable. Direct preference optimization, or DPO, was introduced as an alternative to the likes of RLHF and aims to be more direct and stable than those methods. So how does DPO work? Well, the DPO solution is derived from a key mathematical insight that connects the reward function to the optimal policy. It begins by formalizing preference using the Bradley-Terry model, which states that the probability of preferring a winner over a loser is the logistic function of their reward difference. The sigma here in the first equation is the logistic sigmoid function, and the R star function is the reward score for input X and the response Y. The crucial step in deriving DPO is recognizing that the optimal policy for the KL-constrained reward maximization objective has a known analytical form. It's proportional to the reference policy and reweighted by the exponentiated reward. By rearranging this equation, DPO defines the reward function implicitly, using only the optimal and reference policies. Substituting this implicit reward function back into the preference model gives us the final DPO loss. Let's delve a bit deeper into the details of this loss function and how it works in practice. At its core, the DPO loss is a weighted binary cross entropy loss. The term inside sigmoid function here can be thought of as an implicit reward that we mentioned before. It measures how much the log probability of a given response has increased under a new policy compared to the original reference policy, scaled by this hyperparameter beta. The DPO objective then simply tries to maximize the difference between the difference between the implicit reward of the winning response and the implicit reward of the losing response. So how does this translate into training? Well, during backpropagation, for each preference pair, the gradient effectively does two things. It increases the likelihood of the preferred sequence, YW, and decreases the likelihood of the rejected sequence, YL. The magnitude of this update is implicitly weighted by how surprising the current probabilities are, you can say. Because if the model already assigns a high probability to the winner and a low one to the loser, the update is small. But if the result is surprising, i.e. the model assigns very wrong probabilities, and then the update becomes bigger. The hyperparameter beta is crucial here because it plays the role of the magnitude of the KL divergence constraint from the original RLHF objective that we looked at before. A smaller beta allows for larger deviations from the reference policy, while a larger beta keeps the fine-tuned model closer to the original. The intuition here, to summarize the intuition of DPO, is that instead of training a separate reward model like RLHF, we are directly optimizing the language model policy on a simple binary cross-entropy objective. This elegantly transformed the complex multi-stage RL problem into a single-stage supervised style classification task. And while DPO offers some advantages compared to the likes of RLHF, it's worth mentioning that it's not a perfect method. Let's explore some of that. So first, DPO has been found to be prone to overfitting, similar to RLHF. And this is a mathematical consequence of its objective function, because DPO's implicit reward is unbounded. So a finite dataset where one response is always preferred, the reward can approach infinity, nullifying the KL regularization term, or the beta parameter in the case of DPO. An alternative method, which in part attempts to improve upon this, is identity preference optimization, which uses a fundamentally different objective function that is mathematically bounded, ensuring that regularization remains robust. The second problem with DPO is that paired preference data is expensive to acquire, since it in principle requires human labeling for two alternative responses, at least if you want the labeling to be accurate and of high quality. Automating away human labeling is something I've have a lot of experience with, as I mentioned before, with the AutoGrasper toolkit. So I understand the frustration that comes with this problem. And a notable alternative to DPO, which aims to alleviate some of the issues of this problem, is the Kahneman-Tversky optimization, or KTO. This learns from a much simpler binary signal, where individual examples, instead of paired examples, individual examples are labeled good or bad. And the KTO paper also introduces the idea of human-aware losses, arguing that we can actually design loss functions based on models of human utility, like prospect theory. While this simplifies data collection, it also introduces a new hyperparameter in the form of the desirable threshold, the optimal setting of which is still an open question. Moving on to another central point of interest in the field of preference alignment, which is evaluation. Turns out that defining a good gesture is quite difficult because key qualities are quite confounded. A gesture can appear human-like, but be completely inappropriate for the accompanying speech. Furthermore, different studies often use different datasets and evaluation methods, making direct comparisons of models nearly impossible, which is also a very prominent problem in the field of robotic manipulation, which I've experienced with, so I bring it up. This problem, in the context of alignment, is attempted to be solved by the Genea challenges, which introduces a standardized benchmark to disentangle these qualities and allow for rigorous, reproducible progress. The core of the Genea evaluation is its mismatching methodology. To judge human likeness, evaluators see silent motion. To judge appropriateness, they compare a gesture with its correct audio versus a mismatched audio track, which penalizes systems that produce generic, meaningless motion. In 2023, the Genea challenge moved from a single forced choice to a 5-point scale to gain more granular data. But the most significant evolution, and the one that I'm most interested in, was the introduction of a dyadic interaction context, which we saw on the previous slide. The benchmark now explicitly evaluates appropriateness to the interlocutor's behavior. Models tested on this metric showed relatively poor performance, which I thought was interesting because it suggests that current models may lack a deeper causal understanding of conversational function and semantic feedback. Which brings me to a possible synthesis of these topics, as I see them as quite complementary. As DPO provides a stable way of training on preferences, or DPO and its derivatives, I should say. And the GenAI methodology provides a rigorous way to collect them by offering an evaluation framework. So I think an interesting avenue for future research is the combination of these two approaches into a synergistic feedback loop. We can use the dyadic GenAI framework to gather preference data on interactional appropriateness. For instance, that a listener nodding along is preferred to head shaking or generic swaying. And this contextual data is the ideal input to fine-tune, or I hypothesize that it would be the ideal input to fine-tune a gesture model conditioned on the full conversational state, using a DPO style objective. And hopefully this would imbue the models with the more contextual data that could have been the reason why they performed poorly on the GenAI benchmarks. Looking even further forward, I would like to share a high-level outline of 3 research directions that I'll go over briefly, building on this synthesis. This is, of course, a very preliminary outline, open to feedback, which I would love to receive from you. Stage 1, or idea 1, is to develop a 3D gesture generation model that is optimized directly against a novel learned metric for dyadic appropriateness. I propose to train this metric using a contrastive learning framework. Why this, I'll go into more later. Using the GenAI challenges matched versus mismatched interaction data. This approach trains a highly specialized perceptual metric model and would be not a general purpose reward function, but its sole purpose would be to solve a very specific complex classification task, distinguishing a coherent matched dyadic interaction from an incoherent mismatched dyadic interaction. The policy, which would be the gesture generator, is trained using gradient-based optimization with a perceptual loss. So this is a hybrid approach where the generator is trained in a supervised manner, but one of its loss terms is the output of another neural network, which would be the frozen metric model MDyad, which have been trained with contrastive loss. The generator's output is passed through the metric model, and the resulting score is used to compute a loss. Because the entire pipeline is differentiable, gradients can actually flow back from the metric output all the way back to the generator's weights. This is distinct from an RL loop by having this gradient flow from end to end, and is a direct application of the backpropagation to a composite function. This approach is specifically designed to leverage the unique data structure of the GenAI challenge, which gave me the idea of contrastive loss, because the data is structured as interaction, context, matched gesture, and mismatched gesture, which is quite a natural fit for contrastive learning, as I see it, sorry, where the matched pairs serves as a positive example, and the mismatched pair serves as a hard negative example, which is a different learning paradigm than the ones used to train a standard RLHF reward model, which typically just maximizes the log likelihood of the preferences under a totalitarian model. This approach treats the metric as a differentiable loss function overcoming to summarize, this approach treats the metric as a differentiable loss function, overcoming the scalability bottleneck of human evaluation, and allowing for direct gradient-based optimization on the problem of interactional continuity. And I'll be very interested to see how well this would work in practice. The second idea, building upon this, is that with this metric, providing a fast proxy for human judgment, a second stage would use it to guide an uncertainty-based active learning framework. The system would then select the most ambiguous interactional examples for human rating, maximizing the information we gain from each annotation. So this would be a sort of efficient data curation. Finally, this curated data from stage 2 will provide the foundation for my final idea, which is a KTO-style objective on simple binary labels to build models that are controllable by design. So the very cool thing about this, it would work in practice. I'm very curious to hear your thoughts. The cool thing about this is that it would allow us to learn a disentangled latent space from latent space of gestured styles, reframing alignment from a corrective process to an intrinsic property of the model itself. Ultimately, these 3 ideas aims to move us from creating agents that can simply talk at a user to agents that can have a genuine, socially contingent conversation with the user, enabling hopefully more effective virtual tutors, more believable game characters, and more trustworthy robotic assistants, both virtual and embodied. Thank you so much for listening, and I'm very much looking forward to hear your thoughts. Have a nice day.